It's a welcome quiz.
Oh, you guys have to.
All right, let's get started. So just a reminder, we'll have our welcome quiz today. So nothing difficult. So we might go long in lecture. So yeah, we're going to try to clarify. I gathered on Tuesday that people were having issues with the calculations in lab. So we're going to try to clarify that today and do a lot of practice problems. All right, so we left off, and again, what type of a reaction do we have going on here? We have sodium hydroxide, nitric acid. So we have acid-base reaction, and then let's get a little bit more specific with that. So are these strong acids, weak base. What is it? Is it? So, right, don't forget your cheat sheet from last quarter. Maybe if we need more of those. Right, so we got to remember who's a strong acid and who's not. So nitric is one of our strong acids, right, fully disassociating. Again, that's what we're trying to get at. And so I'll just put that, right, SA for strong acid, and then sodium hydroxide, I'll just put SB for strong base. And so, right, we're not thinking of equilibrium or Henderson-Hasselbalch. All we're trying to do is calculate, right, our moles at each point. And this is also where the dilution is going to come into play. So just start off with that, right? So set up your moles initially, and then, right, think back to what your pH is asking for. Well, pH is my negative log of my hydronium concentration, so again, in molarity. And so we'll talk about the lab, but this is something that you'll have to do in your lab. Probably you'll want to do it on Excel so you don't go insane, right? But you'll have to recalculate your volumes too with each subsequent addition, right? So you have your correct molarity. So try to start off, so just, right, figure out how many moles we have initially, and then we'll keep working through this together. All right, so how are these calculations going? So how many moles of sodium hydroxide do we have? Just right initially. Huh. 0 point, I don't think that's, it's a little off because we got to multiply, right, our molarity by our volume. So, right, clear those cobwebs, molarity is just moles over liters. So we have a 50 ml sample, right? Convert that to liters, so 0.05 liters times 0.2 to get moles. So now we should have 0.01 moles of NaOH. And then so looking at our A scenario, how much of our nitric acid, how many moles of nitric do we have then? So 0.006. And then, right, we'll just put none and none, because this is, again, just kind of our initial conditions before we've even mixed them. Okay. And so now let's do change or reaction, however you want to think about that, equilibrium at this point. So now you're doing just the moles, right? So you're going to consume all of your nitric acid, so that's going to go to 0. And now I need to do little math, so minus 0.006. So left with 0.004 moles of NaOH. And then, of course, right, we make 6 millimoles, kind of irrelevant, 6 millimoles. Not that these species matter, right? So in this case, they don't matter because, again, our salt is neutral. So neutral salt, right? Again, strong acid, strong base, so we don't have any equilibrium to consider. And so now where do we go from here? So it's asking for pH, so how do we get pH from this? So yeah, we got to get molarity, so good, right? So let's not forget that, and maybe like star that somewhere, star that on your lab, right? Don't forget to recalculate molarity. All right, so then what's our new volume? So again, we had 50 plus 30. So we're at 80, so 0.004 moles over, I want to convert it to molarity, so 0.08 liters. So now I get concentration of sodium hydroxide. All right, so we're at 0.05 molarity, again of NaOH. So maybe we can't quite use this relationship, but what other formula do we have that's super similar?
POH?
Yeah, so the POH, do you remember the rest of that? POH equals remember, it looks just like this formula, except negative log of now hydroxide concentration. So we can just plug that in now to find our POH. And so then get this for POH, and then I'm just going to do 14 minus that to get our pH. So about 12 point, well, giving it 2 after the decimal place, but then we have to round up, so probably 12.70 for our pH there. All right, good. Any questions on that?
How do you get that
Oh, just the subtraction, right? So then we set up our initial conditions, and then we're seeing, okay, we have less acid than NaOH, so this is going to be fully consumed, and then I just did the subtraction, right? 0.01 minus the 0.006 to leave us with 0.004 moles of the NaOH. And so again, right, this process of figuring out how many moles and then how much, obviously you're doing the opposite, right? So you started with moles of acid. We can go back and forth with this. Right, but it's the same process for this one. So you're going to have your initial moles, obviously, of HCl. You'll calculate your equivalence point. And then, right, you're just doing that with each subsequent addition. So we might come back to that and do an example. But let's keep working. Oh. So before we move on, so what do we say about this one at the equivalence point? Again, strong base, strong acid. What do we need to say at the equivalence point? What's the pH? Don't overthink it. Sorry? But what would it be, though? What's the answer? What's the equivalence point defined as? Yeah, neutral. So exactly, right? So we have the strong base, strong acid scenario. So then, right at the equivalence point, and this is just by definition, our hydronium concentration, or actually we should just say more accurately that our acid species equals our base, right? So however many moles we have of each, and then since it's a strong acid, strong base, the pH is just 7, right? So they're equal. So now let's look at our next titration scenario. So again, right, separate these in your mind. So that was strong acid, strong base. So now let's figure out how to deal with our equilibrium. And again, that's just the Rice table, right? So it's just Rice tables again. And so again, we have our titration, so definition point, so at our equivalence point, our moles of our acid equals our moles of base, and so then our solution has our conjugate base ion, so we will have to figure out, right, what the pH contribution of that. So it's not as simple as our, again, strong acid, strong base, right, because the problem is then we have our conjugate base, right, that's going to go ahead and potentially react and reform that acid there. So that's going to cause, right, a little bit of adjustment in the pH, so we'll look at that and how to deal with that, because that's a specific scenario. And then beyond the equivalence point, which is again what you're doing in your titration, then you're just treating it like a POH problem, right? So then you're just doing the neutralization, figure out how much hydroxide you have left over in excess, and then it's POH, essentially. And then other points, of course, right, initially, the pH of our weak acid plus our strong base is just our weak acid solution, right? We did that last quarter. So then we just do our weak acid equilibrium, again, right, taking into account the Ka. and then we can treat it like a buffer before the equivalence point. And so that is when you can invoke, right, Henderson-Hasselbalch in just that specific scenario, right, when you're titrating, and then you can compare, right, the moles of the base versus the moles of acid, and use Henderson-Hasselbalch. And then we'll work through this today, but again, by definition, our half neutralization for our weak acid, strong base is going to be equal to our pKa there. But like I said, we'll prove it so you can see just the math of it, how it works out. But then by definition, like on an exam, you could just use that. All right, so let's work through that. And so let's just start with A. So write A, we're not asking for pH there, so just reaching equivalence point. So just start with that, and we'll go from there. All right, so let's just start off with A. I know you're probably not that far, but I want to do A, and then I want to show you how to calculate the pH. Even though it doesn't ask for it in this case, it is covered on your homework. And so what do we get for our volume then? So walk me through. So 40 milliliters of our nitrous acid. And then, so how many moles did you get from that then? Oh, so 0.004, right? How many zeros? So 2 zeros, 0.004 moles initially. Good. And so then trying to figure out how many milliliters we need for our 0.2 molar solution. So how many milliliters does that come out to? So we need 0.004 moles of KOH. I'm just setting up my algebra for X. So what does that give us for X? .02 liters or 20 milliliters. Excellent. And so yes, that is all that this problem asks for, but I do want to go ahead and calculate the pH here, because again, it's not trivial, right? So even though our moles are equivalent, let's think about what happened in this reaction, right? So we have our nitrous acid plus KOH, do our double displacement, so make water, but then we're left with potassium nitrite, right? Or, just caring about the nitrite. And obviously, this is our conjugate base species, right, of our acid. And so now let's think about what happened. So, okay, we did our reaction. And so we had 0.004 moles of our acid plus 0.004 moles of our KOH. And so then how many moles of our conjugate base species are we making then? Yep, so 0.004. And again, right, I'm starring this, so this is our conjugate base species, right? So again, nitrate is a base. It's not innocent. So going back to the salts as well, right? Thinking about, okay, yes, this is a basic salt. And so now we basically have to do a KB problem. And so, right, let's calculate our new molarity. So this was moles of our potassium nitrate. And so what's our new molarity? So 40 mils plus 20 mils, so 60 divided by 0.06. All right, so now that's our molarity. Or again, right, our potassium nitrate. And so now we're ready to do just a good old equilibrium problem like we've done before. So let's get, so you'd probably find the Ka of our nitrous acid more readily. So I know we have that in our old notes somewhere. So let's see, nitrous acid here. Let's see if I can remember that. I'll just remember the pKa 3.34. So pKa 3.34. And so then, right, if this is our pK, if this is our Kb, right, conjugate base, then you can solve for your pKb for that. So do you remember what that relationship was? Our conjugate acid, conjugate base.
pH is equal to the pKa plus the log of the base of the acid.
So that's Henderson-Hasselbalch. Not in this one. We're trying to find our pKb from our pKa. Remember that relationship?
Is it pKa plus Kb equals 14?
Yeah. So that's the easy one to use. Otherwise, it was right the Ka times Kb equals Kw, but that's much more convoluted than this one. So yeah, now we can get our pKb much faster. So 10.66, so that means, let me get my Kb. So 10 to the power of negative pKb. All right, so now that's my or my KV, sorry. 2.19 roughly times 10 to the negative 11. All right, so now we're ready to do our Rice equilibrium, right? So it's just like we've done with all our weak acids. So we are ready. So now let's just set up what our reaction is formally. So, okay, again, this is a base. So it's going to react with water to reform our acid, and then leaving us with, again, the definition of a base, some hydroxide. So we need to figure out, right, our pH. And so now here we go. We have molarity. So 0.0667. And then, right, this should look like a Rice problem now. And so change, right, minus x plus x plus x to see how much is going to disassociate and how much hydroxide we're going to form. And then equilibrium, right, 0.0667 minus x, x, x. So now we're ready to solve. So x squared over 0.0667 minus x equals our KB, which I already forgot, 2.19. And then I'll probably take a little liberty making our assumption. So assume 5% to give me x squared over 0.0667. And so now we can solve. All right, so now that's equal to x, which again, right, was our hydroxide concentration. And so now let's get POH from this. So 5.92 for POH, and then 14 minus that. So about 8 then for our pH. And right, so just kind of sanity check yourself, like, yes, this makes sense. So again, just kind of think about what happened. We had our weak acid plus our strong base. And then, of course, in turn, right, we made a bunch of nitrite salts, which again, right, basic salt. If it's a basic salt, then it's going to probably turn your pH a little more basic. And that is, right, what we found exactly. And so again, right, this is just telling you to keep in mind, even though our moles are equivalent at our equivalence point, again, by definition, with our, so again, maybe you want to write, this is my weak acid and strong base scenario. So, okay, even though, right, moles are equivalent, we have to, again, keep in mind the conjugate base that we made. Does that make sense for that one? And for these kind of weak acid, strong base. So again, just kind of keep thinking about those differences, how at the equivalence point, when we had our strong base, strong acid, again, right, we're making a neutral salt, so it has absolutely no influence on the pH. All right, so let's keep moving forward. So see if you can try B. And so again, right, B is going to be a little reflective of what you're going to have to do for your calculations with the vinegar. So see if you can at least start it, right, do the reaction. and think about what formula you could use to help you. Hint, hint. Maybe I'll just write it, right? This would be HH time, Henderson-Hasselbalch time. So I'll give you a few minutes to try that. All right, so let's see how we're progressing on part B here. And so as usual, start by just setting up our reaction, what we're doing. So, okay, we have our nitrous acid plus our strong base, KOH, to give us our neutralization, water, and then plus, again, our potassium nitrite, again, non-innocent, right? So this is our, again, however you want to call this, either A minus if we're calling this HA, so our conjugate base species. And again, kind of thinking about how we'll use Henderson-Hasselbalch once we do the reaction. All right, so let's look at our initial moles. And well, I guess we can use what we found, right, from our first part. So we still have 0.004 moles of our nitric acid. And then how many moles of KOH do we have? So 5 mils, so 0.005 times molarity. So how many moles did that give us? So 0.001 looks good. And then again, right, we haven't reacted yet. And so now let's do change, or again, right, reaction in this case. And so again, just looking at what's going to happen, obviously our KOH is going to be consumed, and then leaving us with 0.003 moles of our nitrous acid. And then of course we'll also make 0.001 moles of our conjugate base species. And so now again we're kind of hinting at Henderson-Hasselbalch now, because we have our HA concentration and then our base concentration. And so then, right, just kind of thinking about where we're going and what we need to consider. And so, right, I don't want us to forget about the volume, but at the same time, if you're thinking ahead to the Henderson-Hasselbalch equation, so pH equals pKa plus my log, right, base over acid, we're going to find our new moles, or molarity, right? Or if you were to do that, I should say, you have your volume like so, right? So notice that volume cancels. That's all I'm getting at and trying to say here, is that in this case, volume's kind of irrelevant since it cancels out if you plug it into Henderson-Hasselbalch. But I still kind of want you to be like aware of the volume thing, right? So you don't forget about it when you're doing your other calculations, but just note, okay, volume does end up canceling out here. So I'll say, don't forget about new volume. But it will cancel in our Henderson-Hasselbalch. So just keep that in mind, right? So if you use Henderson-Hasselbalch, then you don't really have to worry about that. We could, right, at least just state for the record our new volume was 40. But again, right, our molarity, if we're dividing both of them by 0.045 liters, then it doesn't matter. All right, so now we can just plug these values in to Henderson-Hasselbalch. And oh yeah, we got the pKa of our nitrous acid earlier, so 3.34. So now we're ready to plug this in. So pH equals 3.34 plus my log of base, which was 0.001, over our acid, 0.003. So again, just pulling those numbers. And again, you're kind of mentally dividing that, yes, my volume didn't matter. All right, so let's see what that gives us. And so I get a pH of 2.86. So is that what other people got for that one?
Yeah.
Sweet. Questions on this one? It's not too bad. And again, right, you're going to be taking the same process for your vinegar calculations, for your titrations, right? So now you're kind of thinking about the lab. And so again, right, just kind of thinking. So obviously, right, initially, that first step before you even add any you have to do a Ka equilibrium, right? Set up just like before, and calculating molarity in mind. But then after that, right, so once you start doing these additions, then that's all you need to keep in mind is how much conjugate base you made. So again, kind of thinking about maybe how you'll set up Excel, you want to set up, right, like how much conjugate base formed would be my suggestion. And then, right, you'll do your subtraction. So then you could figure out, that doesn't make sense. Let me put conjugate or A minus, right? So then you'll be comparing A minus versus HA left, essentially, up until you get right to the equivalence point. And then equivalence point should have been calculated in pre-lab. I don't have the answer on top of my head. We could calculate it, but right, then you go take this all the way up to equivalence point. And then remember, the equivalence point is going to be weird. So again, right, don't forget that equivalence point. Then you have to treat it like we did over here, right, as a KB problem. So then taking the acetate at the equivalence point. Makes sense? All right, let's keep, I'm going to try to do some more sample calculations. I just want to finish. So let's get the definition here. So again, let's just go through this now together, kind of for time's sake, so we could see, again, how we're going to use by definition in the future, because I want y'all to believe me. And so let's set up our situation. So again, it says we want the pH at 1/2 the equivalence point. And so that means we are saying, and maybe let's set up our reaction so we remember what the heck we're doing. All right, so then at the half equivalence point, so by definition, we're saying that our HA is equal to half of our base. Again, this is just moles, right? Stoichiometrically wise, we're not getting into the pH. But let's think about how that would work then, right? Yeah.
Are all these notes on Blackboard?
Yeah, so they should be updating live currently. Let me know if they're not. But yeah, they're all being updated. And so then let's do our kind of example. And then again, we'll see that it's just the pKa. So just thinking through, we had initially 0.004 moles of our nitrous acid, right? We established that. So then at half the equivalence point, that would mean we have added 0.002 moles of KOH. Again, that's just by definition. And so then go through in your mind right now, then the reaction. So now we're going to react, right, or change. Well, that leaves us with 0.002 moles of our acid. Obviously, we consumed our KOH. But then the key point is that, well, at the half equivalence point, we also made 0.002 moles of our conjugate base species. And then, oh, now we're at, right, by definition, what is the log of 1? If they're always going to be equal, right? Log of 1 is 0. So now we're back at our definition. So again, right, we could now prove this. So pKa plus my log base over acid. But then again, at half equivalence point, right, my base equals my acid after the reaction, right? Is what we're really saying. And so then we're just left with the pKa then. for our answer, so 3.34 there. So does that make sense for that one? So again, on an exam in the future, right, you can just write, you know, half equivalence point equals the pKa, and you don't have to give me a bunch of work for that, right? You don't have to prove that to me. So that's just by definition. All right, let's try to run through maybe a few sample calculations. So where do y'all want to start? What's giving you the most issues with the titration? So I know half of y'all haven't done it, but maybe you at least thought about the calculations. And so again, things to think about, because I really would put it on Excel. So then you probably want to think about, oh, no, I don't want to do that, cancel. You want to think about, right, setting it up. And let's see, so the initial pH, right, shouldn't be too bad. So I don't know if you want to walk through that calculation or not.
We walk through that.
All right, so, right, we have initially 10 mils of our 0.01 molar solution, but then we added it, right, to about 90 mils, so we have 100 total for our volume. So this is where you're already thinking of volume. And so then how many moles is that? And so we have to calculate, right, our new molarity essentially. However you want to do that. So for this initial one, we could do, since we're just doing a dilution, C1V1 equals C2V2 is probably the fastest way to recalculate our molarity. So 10 mils of a 0.01 solution, and then now I have 100 mils though. So that means we have a 0.001 molarity. And so again, right, just kind of, I don't want to do this all for you because I think there's a huge value in Excel, but just kind of think about, right, like what you need to do. Maybe initial moles, because you'll have to calculate, right, how much is subtracted at some point. And let me just recalculate those initial moles. So 10 times 0.01, right? So we started, bless you,
Thank you.
with 0.1 moles. And then, right, you also kind of want to keep your volume total somewhere. Okay, and we had 100 initially. Maybe you want to think about having a molarity one. So molarity is obviously equal to moles over liters, right? Just kind of thinking about how you could set it up. Then you got your pH, so you're not doing this all day. It's great practice in case one day, you know, you become a professor and then you calculate all your grades manually, like I do. So then, right, there's our 3, which is what they have here. All right. And so then let's just do a sample calculation. So let's say you added, right, exactly 1 mil total then of NaOH. So now we have to keep track of our subtraction. And so again, right, you can rearrange these columns a little. Now I want to move these over. Oh, wrong way. Sorry, painful to watch other people do Excel. And right, so then maybe you have a column for NaOH, either moles or however you want to calculate that, right? So I'll leave that up to you before, again, you watch me painfully do this. But essentially you have to get, and so I would probably separate it out by like NaOH volume, NaOH moles, because right, you're going to need to also keep a running total of your volume. So again, I don't want to spend forever setting it up, but now let's go through kind of our calculation of what we have to do. So if we added 1 mil, again, we just need to do the reaction. So 1 times 0.01. So we added 0.01 moles. And so again, right, we need a moles of NaOH added. So 0.01. Oh, I didn't do that right. I knew that sounded weird. 0.001 times 0.01. That makes a lot more sense. So right, 1 times 10 to the negative 5 moles. And now you do your reaction. And so that's again, right, you have your initial moles. So 0.1 minus my answer. So that gives us, right, moles of our HCl left. But then you have to calculate your new volume. So divide it by, in this case, 101. So now, new molarity. I did something wrong there, probably. How did I get that? Sorry, it just seems funny. I'm trying to see what I did wrong. So divided by 0.1. Oh, no, I screwed up my own calculation. All right, bad example. All right, sorry, I'm trying to recalculate. So initial moles, so 0.01 times 0.01. That's how many initial moles we had. That's why something's off. 1 times 10 to the negative 5th, right, divided by your new volume. So new molarity, so now negative log of that gives me my new pH. And then you just keep doing that. So I think I had the initial moles wrong. That's what happened when I was trying to do this. Because the initial moles should be 0.01 times 0.01. All right, so obviously I have to fix my Excel graph. But does that make sense, like each subsequent step? No? Yes, no? I think you guys just got to spend time with it. So it is tedious. But yeah, you got to do it. So I would do it in Excel. All right, well, I have to fix because I messed some stuff up. There we go. That's fixed at least. And then, right, again, so you'll need a running volume total. And so I don't know how y'all kept track of it, if you did it like how much you added each time or the total, but just make sure that it's the total volume at all times. So again, right, you just have your initial moles of HCl, do your reaction by how much total NaOH added, and then obviously new volume. That gives you molarity. Then that takes you to the equivalence point. So equivalence point, right, you don't really need to show any work for that. So 10 mils, right, 7 for our pH, since it's a strong acid, strong base scenario. And then afterwards, you're just figuring out excess hydroxide, right? And so then it turns into a POH problem, which we could do a sample if we wanted, or. All right, so let's do a sample. So let's just jump ahead. So let's jump to 12 milliliters of NaOH. And so again, right, you have to do your reaction. And for Excel, you might want to have probably like different scenarios, right? So you want to set up your calculations before the equivalence point, and then kind of after the equivalence point. So we still have initially 1 times 10 to the negative 4 moles of HCl. And so then we said, well, let's go past the equivalence point. So figure out how many moles of NaOH that is. So 0.012 times 0.01. And so note how that's bigger than, right, what we started with. And so now we can subtract the acid moles from that. So 12 moles of NaOH gives us 1.2 times 10 to the negative 4 moles of hydroxide. If you need to sketch it out, right, as your neutralization reaction, do so. All right, so then we can see, well, all my HCl was consumed, and then we are left with 2 times 10 to the negative 5th then for our NaOH concentration. Obviously, the salt doesn't matter because it's a neutral salt. And then new volume, so we're probably at 112 for our volume. So divided by 0.112. And so then, right now, this is a POH problem, so 1.79 times 10 to the negative 4. So now we can solve for POH, right? And pH. And so now at this point, it should be 10.25 for the pH at 12 mils, theoretically. So feel better about those calculations. And then again for these, at least for this one, if you're using Henderson-Hasselbalch, right, you don't necessarily have to worry too much about the total volume since that's going to cancel out. So you just want to figure out how much is reacting, right? So we could go through, let's try to go through one of these. So maybe let's check out 4 here, just try to do a spot calculation. And let me set this up again a little bit better. So we have to figure out how many initial moles we had. And hopefully I won't screw this up this time. So 0.00118, 8 of our vinegar times our molarity. So we had that many moles to start off with. And again, right, you can kind of think about your Excel chart. I'm not going to painfully make one. But I'm more than happy to help you all later with your Excel charts. 3 times 10 to the negative fourth. Initial moles of vinegar. And so then we said, let's do a spot check here. So we're adding 3 mils of 0.01 molar NaOH. And then let's just keep in mind our volume. Again, it doesn't matter too much for this case, right, when we're doing Henderson-Hasselbalch. We'll need it later once it turns into a POH problem. So I just like to keep it in mind. So we started with 100 mils total. And so again, we're going to be at 103. It's going to cancel with Henderson-Hasselbalch, but I just like to think about that. And so now we have vinegar, C2H3O2 plus NaOH. So then I'm just using this, and again, right, use Excel to help you. I just need to figure out, right, the subtraction essentially to use Henderson-Hasselbalch. So HOH plus my acetate, right, so that's what we care about, our A- species. And so now we're just doing a little math here. So 1.003 times 10 to the negative fourth plus, let's figure out how many moles we added. So 0.003 times 0.01. So 3 times 10 to the negative fifth moles. So do your reaction. So again, that's where Excel is going to be useful. So, okay, now this number becomes our conjugate base, 3 times 10 to the negative fourth moles. That obviously goes away, and then I need to do some math. So that leaves us with 7.03 times 10 to the negative fifth moles. And so then this just turns into Henderson-Hasselbalch. And log of base over acid. What's the pKa of vinegar? Anybody have that handy? Look at my other notes. Let's see. Vinegar, are you on there? Acetic acid, 4.74. I feel like I should have memorized that by now, but I haven't. So pH equals 4.74 plus my log. And again, now we can just take the moles because, like we said, the volume cancels. So 3 times 10 to the negative fifth over 7.03 times 10 to the negative fifth. And so then we have our pH of 4.36 roughly, and let's see if that's roughly what they found here. You know, a little off, but I expect it to be off on the calculations anyways. Well, that looks pretty good. And so again, just keep trucking along like that. And then don't forget, does anybody remember the equivalence point from their pre-lab? Have it calculated? I'm just trying to figure it out really fast. Divided by. So that doesn't seem right to me. Might be right. Yeah, so I think I get like 10 mils as the equivalence point, but I did that kind of quickly. But just remember, right, so at equivalence point, even though the moles is going to equal, you have to treat it like a KB problem, right, taking into account the KB of acetate, which we can at least do that. So we said it was 4.74 or so. So then our PKB is 14 minus that. So probably about 9. Did I dyslexic those numbers? Yeah, I did. You guys gotta help me out. Minus 4.74. There we go. So there's your PKB, 9.26. And so you can use that to calculate your pH at your equivalence point. And then again, afterwards, right, you're just figuring out. So after equivalence point, just figuring out how much hydroxide is in excess. Do we feel kind of maybe better about this? And then, yeah, you'll gotta practice. We're kind of running out of time. I might save, because I did want to go over some of the other homework stuff, but I'm thinking maybe we'll just save it for next week a little bit. Mainly what I was referring to is your homework has some, I'll just show the answers so you can kind of see. What was I looking for? Maybe I'm thinking of another homework. Yeah, I must be thinking of another homework. Now I'm confused. Yeah. So you probably have to look up the pKa, right? So if you remember, we just have this relationship where the Ka and the pKa are related, right?
Yeah.
But if the problem doesn't give you a Ka or a pKa, then you probably just have to look it up. Yeah. All right, that's probably a good place to end. Now I have to look at what homework I'm thinking of. But yeah, just let me know if you need help on the Excel stuff. So today would be a good day to work on that. So like I said, I'll hand out the welcome quiz right now. Obviously, that will be super easy for y'all. I have labs if you need extra copies, by the way. Oh, and then I didn't know if people wanted new periodic tables. I didn't turn off very many, but I can go make some more. I just have 3 extras, but if there's like a high demand, I can go print out a class set. I don't know. All right, let me get your welcome assignment, and then you're free to do what you need to do. Or my suggestion would be to kind of plan out your Excel. Or,
moments.